Hello and welcome back to our final presentation of TWSS 2022. With me today is Dr. David Smith, who has been a very long time employee of the company. And he is here to talk about modeling ohmic surface losses in VSim. With that, I will pass it off to you. Thanks, David, and welcome.
Thanks, Colleen. And thank you to everybody who's stuck around to the last talk for this year's TWSS workshop. So the subject I'll be talking about is modeling ohmic surface losses using the VSim software. There's a little bit of a story that goes along with it. This is work that I've done helping another customer who had to work with this problem. The progress made is likely to wind up in future versions of the software. Let's get into it and start to talk. Most of you who model devices, these are microwave devices I typically work with. Most of you who model microwave devices are accustomed to using the PEC material type. That's the when you set up your simulation geometry and you assign your material property. If it's metal, then you just assign it the PEC, which stands for perfect electrical conductor. And so you don't really see surface losses because, well, they're perfect. Now the code does handle dielectrics with losses. We use that a lot in VSim EM and MD and also in photonics. Metals, PEC type metals, they do have a little bit of conductivity. It's small, and so it's usually neglected, and hence the term perfect electrical conductor. However, in reality, there are surface currents running through the metal. That does cause some loss of energy. This shows up mostly in metallic cavities, where you might have some small surface losses due to the finite wall conductivity. But in most microwave devices, the surface losses are quite small compared to just the hole in the cavity that you're using to couple microwaves in and out. In the lingo, we refer to basically the inverse of the losses is the Q. And so the Q of a cavity might have you might have your external Q, which is the losses due to the hole in the cavity or the couplers. And then you would have your surface loss Q. And Qs tend to add an inverse 1 over QA plus 1 over QB. And in this case, the surface loss Qs are often 10,000, where your external Q might be something like 50. And so you just normally, in the past, we simply have ignored the surface loss Q because we're spending all of our effort on trying to model that coupler accurately to get an external Q. And so, you know, we spent all of our time on geometry and none of our time on this, what is really a material property, since our material isn't actually perfect electrically conducting. In the past, we have occasionally had to do loaded cavities, something like a klystron cavity. The intermediate cavities might have a Q in a couple thousand range, surface loss Q. But that's so high that we've typically done a kludge. We'll take and put an artificial dielectric material in there that has a certain conductivity to give a loss property to the whole cavity. The problem is, and so there's a picture of kind of this kludge, what you would do if you had a cylindrical cavity. Maybe you'd just take and put some of this artificial lossy dielectric on one end. That would give you loading Then you'd run some simulations and you would see how much the cavity was loaded. And then you would tune your sigma dielectric to give you the Q that you wanted. The problem with this approach, of course, is that you have to know the Q ahead of time, and then you're tuning the material property to just artificially match it. And so it's not a first principles technique, it's just a kludge. Give you the effect of surface losses. So recently, I've been helping a customer on an HPM, a high power microwave device simulation. In this device, ohmic surface losses are integral to how one aspect of the device operates. And actually, they probably modify the behavior in other parts of the device, not quite so strongly, but it's probably not there. It's probably, important there too, to some degree. Our project sponsor is aware of this, and he's gotten tired of, asking, did you include surface losses or not? And so the word from our project sponsor was basically, from now on, all HPM modeling will include ohmic surface losses, period. He doesn't ever want to have to ask about it again. So my customer and I go, okay, that's pretty serious. We better come up with something, and it better be, something we can use over and over again for all of our future HPM modeling experience. So that's the situation we were in. This is kind of a picture of part of the device and what really was going on in this case. We have a device to the left, which is not shown here, and then we have an output coupler, a waveguide and coupler. And so I'm showing you a coaxial waveguide here. You can see inside the waveguide on the left here, there are all these little cylindrical little struts. And the struts serve a couple purposes, but one thing that they do is they are very carefully designed. The spacing of the struts are designed so that it matches the wavelength of a particular high order mode that is undesirable in this device, or at least we don't want to be radiating that high order mode. And so a wave will come in from the left, and you can kind of, the picture on the right, you can kind of see it. The wave is a little ugly. You can tell there's more than just a simple wave going on. Then when it hits these two struts, the struts are designed exactly for this one particular mode. And you can see that there's a little stronger fields, and you actually set up a little bit of a cavity just for that one mode. And then the struts themselves are lossy. They're actually stainless steel, whereas the rest of the metallic geometry is copper. And that stainless steel provides enough lossy character to actually damp out this mode that got trapped in this cavity. And so then what comes out on the right-hand side is a much purer single mode, which is what we're after. And so what we want to do is we want to model the behavior of these lossy struts from first principles without having to tune anything. And like I say, we wanted something for this project and really for future modeling too. Now, our customer is an old customer. He's actually using text-based input still, which is getting rarer and rarer. So for him, the solution is a macro file that performs the surface loss computations in a reusable fashion. So what we came up with, this macro and also our benchmarking examples, will most likely be folded into future versions of VSim both in terms of simulation capability and in terms of additional examples. Because of this, we actually designed it to be very fast as we could. We have to obviously do additional calculations to get the additional physical effect. But it's designed to be as fast as we can make it. And indeed, my customer says he doesn't notice the difference when it's on and off in terms of run speed. So that's very good. Benchmarking is ongoing because we want to make sure we really get the physics first principles right, and we match up to analytic results. A little more on that later. So how does the macro work in a simulation? Well, again, this is text-based simulation, so there's going to be lines of input here. If you're familiar with it, then this should look pretty simple. If you're not, it's not that complicated. The bottom line is that there is a setup call for the macro, and then there's a single updater which performs the loss calculation. And the setup call is you have to input the data in a particular manner. It requires the name of the PEC object that you're using in like your Faraday updater, your Ampere updater, your Demetra updater. Those all have to use a single geometric object. So this is the name of that object. Then you can have additional separate objects, and you can have as many as you want, and you list their names just in a list like this. And then you, for each object, you give it the material property. So here I'm pretending I've got a cylinder, a left wall, and a right wall. And so then I might give the cylinder one value of resistance in ohms, the left wall a different value, and that. And this is designed to be very simple to use, and any simulation that creates geometric objects, it's very simple. In terms of how it's used, the single setup call, and then in your standard Faraday updater, where you would have a E Faraday and a Demetra Faraday, simply append one extra updater to that, and that's it. And this is about as simple as it can be, yet as general purpose as we can make it. In particular, there's no functions of space or anything like that. All the spatial character is done by way of geometric objects. For now, we're using in this thing here, these ohm cylinder, these ohms here, we are using what's called the surface resistance, or sometimes called the ohms per square. This quantity is 1 over the conductance of the metal times the skin depth of the metal. The skin depth of the metal uses the conductance itself, but also the frequency. And one of the reasons it's done this way is because this buries frequency into this material property. And we do not have any frequency dependence. So this is really accurate for a single frequency or a narrow frequency range. And so this is how the material property is provided. As I said before, it's based on geometry objects. Each object can have its own different surface resistance. Remember, in the problem we had, I've got some parts of that waveguide are copper, and then those struts are stainless steel. So each surface is going to have a different quantity, and you can have as many objects in the list as you want. Let's back up a second and talk about the physics behind this. If you've never seen it before, it's a little bit different. If you've seen it, then this is probably, old hat. But the ohmic losses, they derive from the surface currents that are running in the metal. basically your surface losses are your sigma times your K squared. But the thing of interest is that the surface current that runs in metal, in a PEC type metal, is actually due to the parallel magnetic field right next to that surface. And so that surface current is actually driven by the B field, not the E field. And this is what's a little bit strange. And so ohmic surface, actually, the ohmic surface losses, they actually go as B squared, not as E squared. And so if you think about it, if you think about one cell in your finite difference calculation, that cell that's got that surface in it, this looks like a magnetic conductivity in that cell. We actually have magnetic conductivities in other aspects of the code, like the matched absorbing layers. And so there's no mystery about how to do that. The only mystery is how to get the numbers right. A little more detail on how you get the numbers right. As I've said before, the surface current is the parallel B field. Current runs in a thin layer called the skin depth, which depends on the material conductivity of the metal and the frequency. Now, because this current is running in a material that is not perfectly conducting, there is an ohmic electric field, and E equals J over sigma, or K over sigma right here. So the normal boundary condition at PEC is that the parallel field along the surface is 0. But once you include surface losses, you actually now have a situation where the electric field is not quite 0. Instead, it's this small number that actually depends on the B field right there. This surface electric field shows up in the Faraday's law in the curl E, whereas when we would cut across the surface and say that's 0, now when we cut across the surface, we actually see that small electric field on that surface. Now it's a little tricky because it includes the actual surface area in the cell, and it includes the cut, if you would, the cut volume of the cell. And so when you put these all together, what this looks like, you pull this term over here, and remember E surface depends on B. And so what it looks like is here is Faraday's law. But this time there's a little absorption term, a little A to B term here. And that's your surface losses. And you have to compute this eta from your surface area and the basically this combination DLH and DA cut is the cut cell volume. So implementation wise, right now we've basically just have a fixed material property, and so we can do all of this calculation ahead of time. And so we do it all at time step 0, and we set up what is basically just a multiplier each time step, which is basically 1/1 plus eta delta t. And we store that in memory for every single B field component. Then we simply multiply that every time step. This uses what's called a field bin op updater, terrible, ugly name. In the code, it looks like this over here on the right. But these bin op updaters are very fast. It's our fastest updater. And so this is what is giving us good performance on this. And that's important to have the generality of arbitrary number of objects, arbitrary material properties, but still have the good performance. There is a lot of work that goes into setting up this little factor of eta. For those who are, familiar with text-based input in this, you see that we're using the geometry updater. We have to do that to get the surface area. Here's the surface area over here, and also the volume fraction. And so we have to do that. But that's not the end of the story. If you think about it, the surface area is a cell quantity, whereas the magnetic fields are phase quantities. And so there has to be this allocation of the surface current from the cell to each of the individual faces, which may be 1, 2, 3, 4, 5, or 6 faces that are non-zero, depending on how the cut through the cell goes. Well, actually, it's 3, 4, 5, or 6. There's always at least 3 faces that are non-zero. But you do have to worry about this face allocation to make sure you get the surface area right. And this is the kind of thing that we want to put in the macro, do it once, and then never have to worry about it again. In addition to, of course, the problem that the customer is doing, I'm also doing some benchmarking to make sure that we're getting the right answer. There are a few cases that have analytic results. The square cavity is easy, but it doesn't really test very well because the flat surfaces aren't really covering the curves that happen in real devices. So the first test you really want to do is on a cylinder, which has at least got some of these rounded cut surfaces. And so there is an analytic result to this. So if you say my cylinder is made of a certain material, you can calculate what the Q of that cylindrical cavity is. Unfortunately, there is some discrepancy in the literature on that analytic result. And I think in the end, I'm just going to have to work some Bessel functions and verify which of the 2 different answers are actually right. So I got a little work to do there yet. So what we're doing here in this example is we just take a cylindrical cavity like you're seeing on the left here, and we pump it up for about maybe 10 cycles. And in this case, it's just the standard TM01 mode, which is just a current from one of the walls, one of the flat walls to the other flat wall. And we oscillate that back and forth about 10 times. That seeds the primary mode in that cavity. Then we turn off the source and we just let the cavity ring. And if we were really using PEC materials, then that cavity would ring forever and ever. And in particular, finite difference conserves energy, and it really would ring forever and ever, and the amplitude would not change at all. But because we have surface losses, those surface losses will absorb energy. And so what will happen is the cavity will very slowly ring down, depending on how much surface loss there is. So let's see here. Oh, and when this rings down, well, we'll go here. Let me see if I can switch. Always dangerous to bring up an active code, but so here again, text-based input. Here is the input file for the benchmark. So I've got some geometry, and where is my, here we go. Here's exactly the lines that I had showed you before. This case, I've got one object, so there's one object in the list, and there's 1 ohms per square for that object. But that's ugly. Nobody likes to look at that code anymore. So we'll just look at the basic parameters. We'll say this is an input file. It's doing a cylindrical cavity, so it's got basic parameters of radius and length. Here's the parameter we're interested in, sigma. That is the conductivity of the material that I'm using. And then there's some other variables, nx, ny, the cells, dm frac, number of periods, etc. So now I'm gonna plug for a new feature that we have in VSim 12. When I ran this, I actually ran it from the Design tab instead of the Run tab. And so in the Design tab, you can pick a variable. Here's those variables: radius, length. And you can pick one of the standard variables, and I'm going to pick sigma, the conductivity. And so what I want to do is I want to run a whole bunch of sequence of runs with conductivity. And then you can take this variable and you can give it a bunch of values. In this case, I kind of wanted a logarithmic variation. So I want to run my sigma from about 0.1 up to about 500. So that's a factor of 5,000, 3 orders of magnitude. And I'm going to do that with 12 runs. And so I set up my 12 runs, and I can just list the individual parameters here, which I've done with the standard 1, 2, 5 logarithmic progression. And this is nice. You hit the run button and off it goes, and it runs 12 runs while you're off getting coffee or whatever. And you get that done. Here is one of those runs. And what you can see when you visualize from a design scan, these are called scans, you can see that you get a little extra button here, and you get to choose which of your 12 runs you're looking at. And so here is my scan run 04. Here's my cylindrical cavity. There's the fundamental mode. What we're really interested in is the history. So this shows the ring up of the cavity and then the ring down. And what's nice is I can go ahead and go to scan 10, run 10, and it will remember which history I was looking at. It will remember which fields I was looking at. And so you can see that run 10, it took a lot longer to ring down. So it's got a much higher conductivity. So then finally, in addition to this, what you can do is whenever you have one of these ring down type simulations, you can use the compute inverse Q. And so there is an analyzer which takes that ring down and converts what the Q is, or actually 1 over the Q. And when you do that, you'll get an additional field. And so here is the result of that analysis script. And it shows you your Q is about 8 times 10 to the minus 3. You notice that it doesn't give you any result until the signal actually starts ringing down. So if you look here at the history, you can see that the signal starts ringing down at about 10 nanoseconds. And so starting at about 10 nanoseconds, it knows that it can kind of make an estimate to the Q. And it's a nice flat value because I've just got a single mode, no contamination. So I can just then take and read that value and compare it to the analytic result. So that's the benchmarking. That's going on right now. When I compare to the analytic result, I'm not perfect. I'm within about 15%. I'm still trying to work out what the last little bit of disagreement is. Like I said, there are issues associated with the allocation from cell to face, and this might be something related to that, or it could be that I'm using the wrong analytic result. So that's still ongoing, but within 15%, it's probably going to be good enough for my testing. So this little short talk. Summarize what I've talked about. Basically, we've got a geometry object-based surface loss macro that has been written, created, used, and benchmarked. It's because of the way it's written, it should be suitable for inclusion in future versions of VSim. It's got a real easy interface, and hopefully that'll facilitate its inclusion in the GUI as well. So then you won't have to look at all the text-based stuff. So thank you very much.
Thank you, David, for doing this presentation for us. It looks like we have a few questions.
Okay, I'm looking at them right now.
All right, I will let you go ahead. The first one about boundaries.
Okay, so from Bob, we've got how might this compare to simply accumulating the Poynting flux E surf cross B across the boundaries? Well, so there's kind of two steps to this question. When you're using a PEC, E surface is of course 0, and so there is no flux across that. As we do this, we are not actually computing an E surface per se. We are folding it into Ampere's law and using that kind of lossy parameter instead. You could, there's nothing that would stop me from producing an E surface field and then trying to look at the Poynting flux that way. And actually, what you're bringing up is a good question, which is we ought to have a history, not yet done, is a history diagnostic that would just calculate the surface loss in terms of watts instead of just the decay signal. So I think actually maybe what you're getting at is I've got a little more work to do, which is to also have a history diagnostic that would actually give me the watts of power lost in the boundary. I hope that answers your question. Ming Che, thanks. What is the difference between your algorithm and that implemented in the Neptune code? I do not know the details of the algorithm that's implemented in the Neptune code, but if they're doing surface losses, they'll have to do something very similar. There isn't really any mystery about what the physics is there. I would, there might be detail in terms of how they're handling the cut cells, and that might be worth talking to them about. And then also for Ming Che, our third question is, normally the Q value is very high, like tens of thousands. And how to determine this Q in time domain? Well, that's easy. That inverse Q analysis script will handle that. And in fact, the examples I was showing, let's see if I can, in the example here, you can actually see the decay. Whereas, as you point out, if the Q is in the thousands, the decay will be, 2 pixels across this whole range here, and you can't even see it with your eyes. However, if it's a pure mode, if it's a good, strong sinusoid with no other contaminations, the inverse Q analysis script will get it right. And I have used it in that case many times.
Okay. If anyone has additional questions, there is a Q&A box, a Q&A icon that you can use to type your question in there. Looks like we have another one from Sergey.
We've got a fourth question from Sergey. Have you performed any grid sensitivity analysis? Yes, in fact, I have. That little 15% discrepancy that's been annoying me. The very first thing I did is double the grid and double it again. And unfortunately, it gives the same answer. So So actually, it is quite grid insensitive already at this point, even though it's not the perfect answer yet. And that's a good point, because as you change the grid cell, all those cuts, all those little cut cells change, all those little D areas change. But in fact, it is remarkably insensitive to the meshing at this point already.
Okay. Another question for you.
Let's see, a question again from Ming Che. Are the dispersion and thickness of skin depth included in this algorithm? No, as I mentioned before, the skin depth is computed from both the conductivity and the frequency. And so that frequency dependence would give you, I think, the dispersion that you're referring to. And so, no, we do not have dispersion. So this is basically single frequency, or what you would call narrow band behavior at the moment.
Let's see. And another question that came in through the chat. How do you get around from resolving the skin depth?
Well, the skin depths in these typical devices, when you're running at gigahertz, the skin depths are microns. And the cell size might be a millimeter, or maybe even 1/10 of a millimeter, which is still 100 times larger than the skin depth. And so there's no way that you can resolve the skin depth with your finite difference mesh. So that's why you're using this, this global model of current and surface area. And we're not trying to do that. Now, if you want to, you want to think about skin depths, don't think, if you want to resolve a skin depth, don't think about a 1 gigahertz frequency problem. Think about a 60 hertz, like your AC current in the wall. If you've got wires in your wall, they're about, this big. And they actually, the size of the wires in the wall is about the skin depth at 60 hertz. But we do stuff at gigahertz here, and so our skin depths are not resolvable.
Great.
Maybe I'll qualify that when we get up to terahertz, then we start worrying about skin depths again.
Sure. So I will put in, just to let everyone know again, all of these videos and presentations will eventually make their way to the TechX website, as well as the TechX YouTube page. So you can go back and view them or work from them. VSim 12 is coming out this week. So we are working to get out evaluations for anyone who wants to try the latest version. If you are a current client or a new client, we want you to try it. And if you are eligible for an upgrade as a current client, we want to make that happen for you too. So please, you can email us at sales@txcorp.com with specific questions. If you have a question about upgrading, and then you can always request an evaluation off of our website as well. So I think that's it for questions. David, thank you again for taking the time to do this for us. And I thank everyone for joining us for this series of webinars that we have. It's always fun to bring everyone together and actually kind of finally show and make accessible all the neat things that we have been doing here. So thank you again from all of us at TechX. Thanks, Dave. Bye-bye.